So in this uh, in this video, we're going to talk about calculating the tangential stress due to bending. So in an earlier video, we defined our tangential stress equal to the negative Young's modulus times the change in angle d theta times the Rn minus R divided by R also divided by theta. So um, the issue is the d theta, theta, and um, elastic modulus term um, will vary depending on your beam. So we're going to try to define it in terms of variables that we know are should be a little bit easier to define for a curved section. Okay, so you want to define this term in terms of a cross-sectional area A, our applied moment M, and our eccentricity E. Okay. All right. So we know that the total moment within our section would be equal to the negative times the integral of y times our stress in sigma theta dA. Okay, all right. So if we plug in our value for y again is the distance from our neutral axis to our point of interest. Okay, um, and then for sigma, we can do the same thing for our equation up top here. All right, we're just plugging it in for sigma theta and multiply by dA. Okay, so we're going to take out all the terms that aren't dependent aren't functions of r. So if we do that, we'll end up getting the moment will be equal to e d theta over theta times the integral of Rn minus R squared divided by R dA. Um, so if we just keep chugging along here, all right, and we multiply out that Rn minus R squared term, we'll end up getting three terms. Okay, so we'll end up getting Rn squared divided by R dA. Um, okay, um, so which ends up with the value of A over Rn. Um, and then if we integrate our second integral, we'll just get the integral will just give us A, and then the last integral will just give us equal to uh, RC times A. Okay, so if we plug those back in to our equation here, we'll get this equation will be equal to our moment. So then we're gonna rearrange everything here. All these terms have a common area, so we can bring the area out. And what we're left with is we're just left with equal to RC minus RN. All right, and then we can replace RC minus RN with our eccentricity term. All right, and then we're going to move all the terms that are not ed theta theta over to the other side, and we can set ed theta over theta equal to the moment of our cross section divided by our area of our cross section times the eccentricity. Okay, so we're just going to plug that in to our equation here for ed theta theta, and now we have our stress in terms of our radius relative to our neutral axis. Okay, so you can also, if you prefer, you can substitute in y being equal to the radius of your neutral axis minus r, and you can rewrite the equation here. Okay, all right. So the equations that we discussed here, they only account for uh, bending bending moments. They don't account for um, axial forces. So you do need to account for axial forces in some cases. So your sigma theta total would be equal to the sigma theta due to bending plus the sigma theta due to your axial stress. right? Now the axial stress is really simple. It's just the force over the area, so it's nothing too bad to calculate. Okay. All right. So we're gonna do a simple example to try and illustrate how you can calculate sigma theta for a curved beam.